All right, thank you so much, everybody, for sticking around till the end of the session. Our next speaker is Professor Synge Todo. Professor Todo specializes in computational physics, quantum statistical physics, high-performance computing, and quantum computation. He has been working on studying phase transition phenomena in strongly correlated many-body systems and in developing novel simulation methods. After working at the Institute of Solid-State Physics, the Department of Applied Physics, and the ETH Zurich, Todo Sensei has been professor at the Department of Physics at the University of Tokyo since 2018. Professor Todo, please.
Okay. Thank you very much for kind introduction. So today I would like to talk about the algorithmic aspect of the classical and quantum computation. So let me start with the classical computation. So here is the recent survey about the classical algorithms. They analyze the data from many textbooks and many research papers and how much the proposed algorithm improve the efficiency of the calculation. So unfortunately, almost half of all the algorithm families, little or no improvement. But some algorithm gives transformative improvements. And they conclude that the algorithms are one of the most important sources of improvement in computing. So this is the classical case, but I think also for the quantum case, the same situation will happen. But I think that the scaling of the algorithm should be investigated or should be checked very carefully. Okay, so let me start about the quantum computing. So as you know, the wave function of n-qubit system can be expressed as a linear combination of many states, 2 to the power of n states. So we have to specify many coefficients to describe the quantum states. Okay, so the memory cost of this is exponentially large if you have many qubits. So this C, coefficient C, can be regarded as an n-leg tensor or rank n tensor. So tensor is actually the multidimensional array, and it's a generalization of vectors or matrices. And actually the zero-leg tensor is scalar, and one-leg tensor is vector, and two-leg tensor is matrix. And this is n-leg tensor. But the problem of the many-leg tensor is the memory cost is exponentially large, and also the operation on that tensor is exponentially computational cost is also exponentially large. And actually, this tensor is, you can find the tensor everywhere. Actually, for example, the probability distribution function in large dimensions, P of S1, S2 to Sn. This is actually a tensor. And multidimensional data is, actually data. And also, the two-dimensional data, for example, image or grid data, is a matrix. For example, the 256 times 256 pixel image is a matrix. But if you represent these indices as a binary number, you can regard this large matrix as a in this case it is regarded as a 16-leg tensor. Okay, so this tensor representation can be found also in, for example, the neural network, where the weight matrix can be regarded as a tensor with many legs. Okay, so next I would like to introduce a tensor decomposition. So tensor decomposition is a decomposition of many leg tensor into product of small tensors. And the connecting legs is called virtual leg. And this means that we take summation of common over these common indices. It is called contraction. So this way we represent a large tensor into a network of small tensors. So this is called tensor network. And advantage of representing a tensor as a tensor network is that, for example, the data computational cost and the memory cost. And for example, the memory cost is reduced to from exponential of n to order n. And another advantage of tensor network is there is a freedom in contraction order. Actually, if you take a contraction of these virtual indices, we come back to the original tensor, but the order is arbitrary. Okay, so there is a possibility to reduce or optimize the cost of the operation. And also, we can introduce highly accurate approximation based on the singular value decomposition. These are the advantages of a tensor network approach. So actually, tensor network can be used as an approximation of the original big tensor. So for example, we can use this tensor network as a variational wave function in the quantum many-body systems. And also, in many cases, we can represent quantum state by using the tensor network with small bond dimension exactly. For example, AKLT state is the example. And also, many quantum and classical statistical model can be represented as a tensor network from the first. And also, as I show later, the quantum circuit can be represented as a tensor network. Okay. And in the field of statistical physics, there are two approaches. One is the renormalization approach. So in this approach, we represent the model or problem as a tensor network, and we introduce some approximation and take a contraction of tensor network to calculate a partition function. And the other approach is the variation approach, where we use a tensor network as an approximate wave function or some target functions. And in both cases, we need to take a contraction to evaluate, for example, the expectation value or some gradient for the optimization. But the exact contraction of tensor network cannot be done in 2 and higher dimensions. So we have to introduce low-rank approximation in general. So that the important quantity is called the bond dimension. We denote this bond dimension d or chi generally. Okay. So this is the standard approach in the statistical physics. Okay, so the partition function of the Ising model, for example, can be represented as a tensor network like this. So to contract of this tensor network to obtain the partition function, first we decompose each tensor into two tensors, something like this, by using SVD, and we only take largest eigenvalues between these two tensors, and contract these 4 tensors, and we have a coarse-grained tensor network like this. By repeating this procedure, finally we have only one tensor, and by taking a trace of that tensor, we will have an approximate partition function. And to improve the accuracy of this procedure, the environment effect is important, and also the removing local correlations is also important. For that purpose, there are many new algorithms have been proposed so far. Okay, but to improve the accuracy, the computer's cost increases significantly at the cost of, But yes, so this is the approach for improving accuracy of the tensor network renormalization group. But recently we approach these problems in a different direction. That is, we reduce the complexity of the tensor network renormalization this is the first approach, and the second approach is the increase the precision or accuracy without increasing the complexity. Okay, so let me explain briefly our approach. Okay, before that, okay, so this is the standard method, higher order tensor network renormalization group method. Okay, so in this case, we introduce some tensors called squeezers to merge two tensors into one. Okay, the advantage of this method is we can apply this higher order tensor renormalization group method in higher dimension, 2 or 3 or 4 dimensions, but the cost is huge. Okay, the computational cost in d dimensions is d to the power of 4d minus 1. Small d is the dimension of the system, and large capital D is the bond dimension. Okay, this quantity controls the accuracy of the approximation. Okay, so this is a standard method, but recently we have introduced some technique called anisotropic tensor renormalization group method. Using this method, that we can reduce the cost from d to the 4d minus 1 to d to the 2d plus 1. So that this reduction of the computational cost is significant, especially for large dimensions. And okay, so here is the central idea of our ATRG. So the main cost in the HOTRG is coming from taking the contraction of these tensors. Okay, so that in general, the cost of the contraction is proportional to the exponential of number of legs appear in the tensor network. So in this ATRG approach, we first divide this 4-leg tensor into 3 and change the order of the tensors, and we keep each tensor the number of legs in each tensor as small as possible. So in this case, we only have 3-leg tensors. Okay, this is the key idea of ATRG, and actually we reduce the cost from d to the 7th to d to the 5th in 2D cases. And actually, if we compare the accuracy of our ATRG with the original HOTRG with the same bond dimension, the accuracy becomes worse. But our computational cost is much smaller than the HOTRG. So if you plot the accuracy as a function of the computational cost, the ATRG outperforms the HOTRG, something like this. Okay, and the other approach is we introduce called BTRG. In this method, we introduce some mean field effect to take the environment effect into account. And it's very simple. We add some additional tensors between the original tensor network tensors, and we keep this structure during the renormalization. And by introducing these mean field tensors, we increase the accuracy very much without increasing the cost. Actually, the cost is the same as the original TRG method. Okay, this is the result. So okay, so you can improve the accuracy. Yes, the cost is the same as the original TRG method. Okay, so by using these efficient tensor contraction or tensor approximation for the tensor contraction, we can simulate the quantum circuit. Yes, and actually the classical simulation of quantum computer is very important, I think. So first, we have to check the accuracy or performance of the quantum algorithm by using the quantum simulator. Okay, this is one purpose. And we would like to understand the limit of the classical computation to know where the real boundary of the quantum supremacy is. And third, since the quantum circuits are the typical quantum many-body systems, so if we can develop the more efficient simulation algorithm for quantum circuit, there is these techniques can also be used in different fields. For example, superconductivity or quantum lattice and other complex systems. And also, we want to understand the essence of the quantum computing that can only be done by rewriting some problems in other form. Okay. Finally, by developing the efficient or very fast approximation quantum simulation method for quantum circuit, we can use the quantum computation. We can use quantum algorithm everywhere before the quantum computers are widely becomes available. Okay, but okay, so I think the classical simulation of quantum computer is very important, but the standard simulation method has a very big problems. Okay, for example, state vector simulation and also Feynman simulation, the cost of computation or cost of memory is exponentially large if the number of qubits increases. Okay, and also in the quantum Monte Carlo method, the negative sign problems is a very serious barrier, yes, for approaching the quantum computer by using the quantum classical simulation. Okay, actually the tensor network, the quantum circuit can be written into a tensor network form like this, and actually one qubit gate is represented by the two-leg tensor, and two qubit gate is four-leg tensor. So for this, for example, for this simple quantum circuit, we have equivalent tensor network like this. And by taking the contraction of this tensor network, we have this value. This is the amplitude of some specific, in some specific basis. Okay. And the good point of the tensor network is, as I already said, the order of contraction is arbitrary. So in the original quantum circuit, the time always proceeds from left to right. But in the case of tensor network, you can take a contraction in any order. Okay. So yes, so that there is a possibility to reduce the cost by considering by optimizing the construction order and approximation and also the approximate contraction is possible. Yes. Okay. So this is the state of the art tensor network simulation. Actually, this paper wins the Golden Bell Prize, which is a kind of Nobel Prize in the computational science last year, and they simulate the very big quantum circuit by using a tensor network method. Okay, so in this paper they take a contraction exactly, yes, but okay, we want to talk about the approximate contraction of the tensor network. But okay, before that, actually, any quantum circuit can be represented in the form of tensor network, but I think it's better if you can transform the quantum circuit into a form that the classical tensor network can be can be calculated more easily. For example, so in many quantum algorithms, we use multiple control operations. For example, CCZ or CCCZ or CCX or CCCX or something like that. And actually, in the real quantum computer, we decompose or we implement this multiple control qubit unitary gate into a set of a sequence of these 1 bit and 2 qubit operations, something like this. And actually, the number of required 2 qubit gate, optimal number of qubit operation is not trivial. But in the tensor network representation, the controlled operation is very trivial. Actually, this CCCZ or CCCX gate can be represented as a matrix product operator with D is equal to 2 exactly. Yes. Actually, by using the tensor network, we can represent, controlization of any unitary or any operator like this by just adding one 2 by 2 by 2 tensor. It is very straightforward. But in the real quantum computation, there is a theorem that the universal controlization of arbitrary unknown unitary operation cannot be implemented by quantum circuits. Yes. So for specific unitary operation Z or X, we can represent the control version of Z or control version of X by using the 2 or 1 qubit operations, but unknown operator, it is not possible. So this is the very interesting property of the tensor network, and so this might indicate that multi-control operations are not good building block of quantum algorithms. Actually, this if-then statement is very, we are very familiar with this if-then statement from classical computer, but using that approach is not very efficient, since these kind of operations can be represented in classical tensor network very well, but applying to the quantum circuit is very non-trivial. This is one comment. So this is the classical simulation of quantum circuit. So this way we can use a tensor network approach for the classical computation or classical simulation of quantum circuit. But the other direction, so this is an example. I borrow this slide from my colleague Tsuyoshi Okubo. So we can embed or import the classical tensor network into quantum computer or vice versa. So this is an example. So here we have a very good approximate ground state or wave function of some quantum system represented by classical tensor network simulation, tensor network, and by transforming this two-dimensional tensor network into quantum gate like this, and adding some additional quantum gate, 2 qubit gates, we further optimize the quantum wave function like this. Of course, the transformation from the classical tensor network into quantum circuit is not very trivial, but there are many methods is under development, as for example as in the Yunok-san's talk. Then after the optimization in the quantum computer, we extract this structure as a tensor network, and we can evaluate physical properties and other quantities by using supercomputer like Fugaku or K or something like that. Okay, so so this final stage, we can also use the Monte Carlo sampling and the other techniques. Okay, this is another approach. Okay, so by using the tensor network method, we can connect the quantum and classical computations. Yes. So, but here I'd like to add another axis. Okay, stochastic computation, and actually, in quantum system and in classical system, the stochastic property is there. Intrinsic stochastic properties. For example, the measurement in quantum system or thermal noise or classical system. But we want to use this stochastic property or stochastic computation in a positive way to connect the quantum and classical more tightly. Okay, and actually, by using stochastic approach, we can achieve many non-trivial improvement of even in the classical simulation. Okay, actually, by using Markov chain Monte Carlo, we can sample from any arbitrary probability distribution. This is very amazing property, but further, by using further technique or ideas, for example, we can sample perfectly independent samples from Markov chain by using the idea of perfect sampling or coupling from the past. Or by using the extended ensemble method, we realize equilibrium state immediately after quench. We don't need to thermalize at each step. Or we can sample the extremely rare events. Okay. Also, if we break the detail balance condition, so the dynamics of the Monte Carlo simulation, we can change the dynamics of the Monte Carlo simulation from the diffusive dynamics to the ballistic one. That accelerates the convergence very much. And also, we can perform the exact order and sampling for long-range interacting systems. Usually, the calculation of energy of the long-range O2O interacting system is order n square, but by using the some stochastic idea, we can perform the Monte Carlo simulation on that long-range interacting system with computer cost of order n without any approximation. Or we can measure the energy also in order n cost without any approximation. Okay, so this is the amazing property of the stochastic approach. So we want to combine these approaches to the quantum and classical computation. Actually, in the Markov chain Monte Carlo, there are several levels we have to consider to achieve a very good, very efficient algorithms. For example, we have to choose the representation, how to represent the original model as a, Also, we have to choose the ensemble or, Okay, so this is called the transition graph, and these are the configuration, and these lines means the transition between the configurations. So to construct the efficient transition graph, we have to consider at many levels, something like this. But here I would like to show the approach. So we want to, so here I introduced the tensor network representation as a representation for the Markov chain Monte Carlo. Okay. Okay. The idea is that, like this. So we have a tensor network, and we, as I introduced before, there is an approximation contraction method, TRG, by using the singular value decomposition. And so there are many ways to approximate this, the tensor network contraction based on the value of the singular value. So this means that number of configurations or number of combinations increases exponentially as we increase the bond dimension D. And on the other hand, the probability distribution function in this enlarged space becomes sharper and sharper. And we perform the MCMC sampling in this extended space. Okay, so this is very similar to the quantum simulation. Okay, so in the quantum simulation, first we encode some data into a very high dimensional Hilbert space and perform a unitary operation. Yes, and so that the measurement with some basis gives a desired result with very, very high probability. Okay, that's the essence of the quantum computation. And here is the similar idea. So we use a very, very big configuration space, but by using the tensor network renormalization idea, we reduce the entropy within this space very much. Yeah, and actually by using this technique, we can eliminate the systematic bias due to the low-rank approximation. So this is a test, and for small d, these lines are the simulation from the original TRG, and the red dot is the result of our simulation. Yes, and this red dot is perfectly consistent with the exact result. Yes, something like this. This is for specific heat of magnetization, and also the good property of our approach is that statistical error can be reduced exponentially as we increase d. Okay, so the MCMC approach, the final statistical error is determined like this. Okay, so m is the number of samples of Monte Carlo step, and tau int is the autocorrelation time. Yes, so this m divided by 1 plus 2 tau int means the effective number of independent samples, and s is the variance of the the original variance. And in many Monte Carlo approach or Monte Carlo method focused on how we can reduce this tau int, yes, by improving the dynamics. But in this approach, we can reduce this s square very much. Yes. Okay, since we are changing the representation, this s square can change. And as a result, the statistical error decreases exponentially with polynomial cost. Okay, and also okay, so maybe, and also this approach can remove some serious problem in standard Markov chain Monte Carlo. That is the negative sign problem. Okay, so this is a very simple model. We apply a pure imaginary external field to the Ising model, and this model suffers from the negative sign problems. In the standard Markov chain Monte Carlo, the average sign decreases very, very rapidly as you increase the system size like this. So the standard Markov chain Monte Carlo simulation is impossible in practice. But by using our method, we can improve the average sign very drastically as we increase D. Okay, for example, even for the largest system size, this purple line is the original standard Markov chain Monte Carlo. But if we take D to 8, for example, the average sign is just 1. There is no sign problem. Okay, so let me summarize my talk. Okay, in this talk, I introduced a tensor network approach that can connect the quantum and classical computation at many different levels. Okay, so the tensor network can be used as a representation framework and analysis tool for pure and mixed states and quantum circuits. And we can use the tensor network approach to the classical simulation of quantum circuits and algorithms. And we are developing more advanced tensor network construction approximation scheme. And actually, there is a strong correspondence between tensor network and quantum circuits. And actually, we can embed a tensor network into quantum circuits approximately. And by using this idea, we can achieve a quantum machine learning or novel classical quantum hybrid algorithms. And also, maybe we can seamlessly offload the task between CPU, GPU, and QPU. And also, considering some stochastic approach, we developed the quantum-inspired Monte Carlo, Markov chain Monte Carlo algorithms. And actually, this new approach exponentially speed up from the standard Monte Carlo method. And also significantly reduce the negative sign in quantum circuits and frustrated spins and fermions and many other simulations that cannot be simulated by the standard Monte Carlo approach. Okay, thank you very much for your attention.
Thank you so much, Todo Sensei, for this really, really informative talk on tensor networks and applications. Is there any question for Todo Sensei?
Yeah, thanks for your talk. It was really nice. Do you have an understanding of what are the quantum circuits that for which tensor networks have a hard time to capture?
Excuse me.
What are the circuits that tensor networks struggle the most to simulate?
Okay, that depends on the, for example, the entanglement or, yes. So so if you introduce approximation to the construction of the tensor network, so the precision or accuracy of the approximation is controlled by how the singular value decreases, how fast the singular value decreases. So that if you have more entanglement between the different part of the system, it's much more difficult to simulate by using tensor network. Yes. Yes, it depends on the structure of your quantum circuit. Very much.
Thanks.
So I guess, Antonio, maybe this is a question to you in relation to your own question. I don't know if it relates when you were talking about entanglement forging and the SVD, right, and the Smith coefficients, right? When you have a maximally entangled state and you start having Smith coefficients that are equally large, right? Basically, on this composition, you can no longer toss any of those coefficients, right?
Yes. I was more thinking about, so there's ways of directly mapping quantum circuit into like neural network. So people that develop like gadgets that allow you like to take a quantum circuit and iteratively build a larger neural network that captures that quantum circuit. And so if you do that, I think people have very hard time with like certain gates. Like for some reason, like the Hadamard gate is very hard for them. So I was thinking if there was something similar here, but it looks like from what you're saying is more just the entanglement that the states has like as it goes throughout the circuit. Right. That's the only quantity that you care about.
Yeah.
Okay. Thanks.
Any other question for Todo Sensei? So I may have a question for you. I'm very, very surprised, actually. It's very striking, the effect that you were talking about on the stochastic sampling for long-range interacting systems, right? And how the scaling becomes linear. As opposed to quadratic speedup. I was thinking if you could combine that on a quantum algorithm, would you expect a better scaling for this overhead sampling, combining quantum, say for instance, like a quantum enhanced Monte Carlo algorithm with the stochastic methods that you mentioned?
Yes. Yeah, I think it's possible, but I've never think about that. So, yeah, it's a very interesting approach. Yeah, and actually, in the classical case, why it's order n? It's very hard to explain, but yes.
Exactly. Yeah, this is what I was thinking. Right? It's like very, very surprising.
Yeah. Yes. So our brain is not enough to. Yeah,
because on the quantum side, right, like the scaling is as well becomes linear, right? And I was thinking maybe you can go sublinear in a combination of the two techniques, right, and speed up. For instance, some of the algorithms that suffer most when benchmark against classical algorithms are those algorithms that only have quadratic scaling, quadratic polynomial scaling, right? And maybe through the combination of these techniques, one can go beyond quadratic speed up. This would be very important.
Thank you.
All right, so if there are no more questions for Todo Sensei, let's thank him again for this very nice talk.